Thank you.
Can I start?
Yeah, please. Thank you. So we're basically 5 minutes late. So I'll.
Yeah. Okay, so we're going to get started. I think this is on now. So our first talk this afternoon is Andrew Stuart from CALTECH.
Thank you. This is my first public talk, including lecturing to students for 2.5 years. So I'm kind of nervous about what it's actually like to be in a room with people, but I'm very pleased to be in a room with people. I'm not an expert in fluid mechanics. So this talk may be a little bit left field for you, but I hope that I will be able to bring you some topics of interest. I'm going to talk about different or new computational methods for representing various solution operators defined by the Navier-Stokes equation. And there are two reasons why I think this methodology may be useful in continuum mechanics in general. One is for learning constitutive models and closures from data. I'm not going to talk about that, but I do have work in that area in material science, and I think potentially it could be useful in turbulence. And secondly, the representations of solution operators that I show you are much faster to evaluate than standard numerical PDE methods. So these are new ways of thinking about how to think about computational partial differential equations, and I will focus on the Navier-Stokes equation, which for the purposes of this talk lead to fast evaluation methods. So the subject of using machine learning and data to find representations of solution operators, which are efficient or discover models that we don't know from first principles, is something which has evolved considerably over the last 5 years or so. These slides are or will be available on the Isaac Newton website, so you'll be able to follow up with all of the references at the end of the talk. But I would like to highlight my collaborators, Kaushik Bhattacharya, who works in material science at Caltech, Bamdad Hosseini, who's an assistant professor at University of Washington, and Nick Kovachky, who is a student at Caltech. Birgitta Lee is a professor here in engineering, and Kamyar is a professor in Purdue. And sorry, that was Birgitta, and Zhongyi is a student here, Kaushik you've seen, and Anima is a colleague in computer science. And most of the talk will be focused on this work, which is with Martin de Hoop, who is a professor at Rice, Daniel Huang and Elizabeth Chan, who are both postdocs at Caltech. So I'll divide the talk up like this. I'm going to say what I mean by operator learning. I will describe a number of algorithms which undertake operator learning, and I will focus for this talk on one of them, which I call the Fourier neural operator, which combines together a number of fast to evaluate computational primitives in such a way that it's possible to approximate arbitrary mappings between spaces of functions. And then, so this will all be quite general and will not be focused on fluid mechanics specifically. But then I will discuss two examples which will focus on the Navier-Stokes equation. One is the operator which takes the forcing of the Navier-Stokes equation and maps it to the solution at a particular time. And the second, which takes the initial condition of the Navier-Stokes equation and maps it to a solution at a later time. And I welcome questions, so please interrupt. And as I said, I'm left field, so things, the way I'm thinking and talking may not be familiar. So please ask questions to clarify things for yourself. Okay, so let me tell you what operator learning is about. But for those of you that want concrete, just think of psi dagger as being the solution operator for the Navier-Stokes equations, which takes its initial condition into its solution at a later time. And that's a canonical example that will help you understand the abstract setting which I'm starting with. So psi dagger is a function or an operator which takes a space of functions u into a space of functions v. And I've simplified the notation for this talk, and U and V are actually the same, just for this talk. There'll be spaces of functions that map a domain D and RD into R. And when I do the Navier-Stokes equations at the end, I will look at the Navier-Stokes equations on a two-dimensional torus, periodic boundary conditions, and I will use a vorticity stream incompressible. I'll use a vorticity stream function formulation. So the function of interest would, for example, be the initial vorticity, and we would be interested in mapping it to the vorticity at a later time. And the concept here is that we want to try and learn a representation of this, which is not a standard numerical integrator, but rather something which is learned from data. So the concept is that we can run a numerical integrator and generate data pairs. So concretely, initial conditions and solutions at a later time for a vorticity stream function formulation of Navier-Stokes equation, with the input initial conditions drawn from a probability measure. And the objective is to try and, on the basis of that data, approximately represent the solution operator. And I've done this in a very simple setting. It's easily generalizable to vector valued functions and settings where these input domain and the output domain, the physical domain, are different. Okay. Any questions on the setting? Okay. So in operator learning, so remember psi dagger is the true operator. What we do is we introduce a parameterized, so here theta is a subset of RP, a parameterized family of maps which take U to V. And the objective is to choose the value of the parameter, or a value of the parameter, so that a function from within this class approximately represents psi dagger, which is this, for example, the solution operator for the Navier-Stokes equation, mapping initial condition to solution at a later time. And we want to do that on the basis of data. And the traditional approach to supervised learning, which we're here generalizing from the standard settings of, for example, image processing, to this setting in which the inputs and outputs are themselves functions, is to try and choose the parameter theta so that from within this operator class psi, you pick a value of theta so that psi picked from this class is close to the truth psi dagger. And remember, we're given data in the form of inputs U to psi dagger. We don't know psi dagger, that's the hypothesis. We know inputs to it and outputs from it, with U drawn from some measure mu. So this is the expected value of the difference between the true function that we want to find and its approximation from this class. And we want to identify the parameter theta that makes this as small as possible on average, averaged over the data. In practice, we have a finite set of samples. And so this, what I've written here, is approximated by an empirical approximation or Monte Carlo approximation. So this is called training, identifying the theta star which minimizes this. There's much to be said about this because for the methods that, or the classes of functions I describe later, identifying theta star is incredibly difficult. Proving that what you identify is a global minimum or close to it is very difficult, rigorously. But empirically, there are methods which do this well and find values of theta star for which, as I will show you, one can match these well. When I do what's called testing, which is to study how well the learnt map approximates the true map psi dagger, I'll use a relative error. So that's just a heads up to note that when we train, we use an absolute error. When I plot testing error to show whether or not what we've learned is accurate, I will do that in a relative sense. Any questions? So I've said why I think this is interesting, and there are many, many possible reasons why this might be useful in continuum mechanics, but the two that I'm focused on in my research program in general are the discovery of constitutive models. And for the most part, I've been doing this for material science problems in which there's a clear separation of scales. But I think there are interesting questions about doing this for closures in problems where there is not a clear separation of scales. And that is a subject area which has yet to be systematically developed. But the methodologies I described could potentially be useful in that setting and potentially useful in turbulence for that reason. The second reason for doing it is that the surrogates that we learn, psi, with the good choice of the parameter theta, can be both accurate and much faster than running a conventional PDE solver. And I will show you speed up of order 500 towards the end of the talk. So this talk will mainly focus on that application, but I am interested in the discovery of constitutive models, for example, in viscoelasticity and plasticity. Okay, so how to represent these functions? What are good choices of size with parameters embedded in them such that they are expressive and can potentially approximate arbitrary functions which are only given to us through data? Well, I'm going to just quickly show you 4 methods that are available in the literature, and they have the 2 properties which are important. Firstly, for all of them, they provably can approximate any operator in some sense. If you impose some compactness on the input space, it's possible to approximate anything. So this is what's called universal approximation and underpins machine learning that you may have heard about in areas different from partial differential equations, in which the machine learning or supervised learning is undertaken between finite dimensional Euclidean spaces. There are, for these mappings, generalizations of those theorems to mappings which take function spaces into other function spaces. And the conclusion is that from within these operator classes, provided the dimensions are chosen sufficiently large, it is possible to approximate arbitrary operators between Banach spaces. So I'm going to just quickly give you a flavor of 3 of them, but then focus on 1. So this PCA method is intuitively, so PCA is EOF. Remember, we're given data which is in the form of many samples from the inputs and the outputs paired together through psi-dagger. This method is quite intuitive. One uses empirical orthogonal functions on the set of data given in the input space to find a finite dimensional basis. Same on the output space. So you project input and output spaces into finite dimensional latent spaces defined by principal components analysis, or EOF, and then learn a finite dimensional neural network between them using standard methods for neural networks on finite dimensional spaces. So I refer to that as PCA-net. And let me just point out that the structure of that is that when you put all that together, the form of the operator that you try to learn is a sum over m, where m is a number of related to the number of PCA basis functions that you use, sum of the product of a function on the input space and functions on the output space. So this is a function that takes inputs u and creates an output function in the span of psi j's, which are given by the EOF on the output space. What's called depot-net does something similar, but tries to learn the representation on the output space from the data rather than prescribe it through principal components analysis. I will not say much about this method that para is for parametric. This is not a good method, but it's something that many people intuitively reach for when they think about trying to approximate functions using neural networks, because it reduces the view I'm giving you of learning operators between spaces of functions to the idea of learning functions which map the product of the input spaces and the physical domain D into the real. This leads to very inefficient methods, which you will see, but so I'm not advocating this method. The Fourier neural operator network is something that I will advocate for in the context of specific geometries and the computations performed here on a torus. And I just want to tell you a little bit about its structure. If you think about computing two-dimensional turbulence on a torus, the method you would reach for would be a spectral method or pseudo-spectral method, and with some time stepping. This Fourier neural operator has the basic ingredients that you would use in a pseudo-spectral time stepper, but puts them together in a different way and represents the operator that maps the initial condition to the solution in a very efficient way. The basic ingredients are a combination of pointwise neural networks. And by pointwise, I mean the same neural networks act at every point in physical space. Linear transformations, again pointwise, the same linear transformation at every point in space. And then a non-local operator, which is based on fast Fourier transform. So in general, some integral operator, and if you make it convolutional, then you can compute it using FFT on a finite number K max of modes. And this is parameterized. And then also this, I haven't said this, but this activation function, which will be a typical sigmoid function applied pointwise, as is typical in neural networks in finite dimensions. So this particular architecture has universal approximation properties. So if you look at compact subsets of Banach space and maps from them into other Banach spaces, by choosing enough parameters in this model, you can approximate any operator to an accuracy epsilon. So it's a very different way of thinking about a numerical method. Let's focus on solving the vorticity stream function formulation of the Navier-Stokes equation. This is a way of computing, given initial vorticity u, one acts with these pointwise neural network, and then you convolve together these transformations, which involve FFT, linear transformations, application of the sigmoid, convolve a bunch of them with different parameters, and then again apply another pointwise neural network. This doesn't look like a discretization of a partial differential equation that you're familiar with, but as I will show you in a few minutes, it produces accurate solutions with speedups on the 2 orders of magnitude. I'm focusing on this because it's the cleanest example in this simple geometry of periodic domain, but many of the things I've just said about the expressivity apply to the other methods as well. So let's look at an example. So I'm going to take the Navier-Stokes equation, and obviously the vorticity stream function formulation goes back a long way, but we've taken the particular setup, scaling, choice of Reynolds number, and example to be close to that in this paper of Rich and co-author Chandler. And in this first example, I'm going to look at the following question. Given forcing, now this is, the equation is written for the vorticity, so this f prime is the forcing in vorticity space, so it's scalar valued function over the torus. I would like to find the mapping from f prime to the solution at time t. And the regime in which we're working, it's not fully developed turbulence by any means, but this is a regime in which the system is chaotic. There are several positive Lyapunov exponents on the order of tens. And so the solution is not steady at time t, but statistically, the t we have chosen, the initial condition has been forgotten. So what do? We generate data by solving this partial differential equation numerically using a pseudo-spectral method on the order of tens or hundreds of thousands of times. Generate that data and then forget about the equation. So the data that's available to us is the initial vorticity and the vorticity at time t. And the initial, the data that's available to us is the forcing f prime and the vorticity at time t. And f prime is chosen to be a Gaussian random field. This is the covariance structure. So this is a field, and so its covariance rather than a matrix is an operator, and it's a fractional, potentially fractional, although in our case, integral negative power of the Laplacian with a shift. So there's lots of stuff to be said about that specific random field, but I'm happy to answer questions about it later. Yes. Yeah, so in this particular case, we fixed one initial datum. So yes, I can't remember what we fixed it at, but it's fixed in this. I will, in the next example, look at mapping the initial condition to the solution at later time. And of course, yeah, in principle, one could do both, but we just haven't done that in this example. So here, the initial condition is just fixed. Thank you. All right, so these are the four methods across the top. This is the forcing, which is a draw from a Gaussian random field. This is the true, as in computed by pseudo-spectral method, output. This is just one example here of one particular input in the form of the forcing, one particular vorticity at time t. And these are the predictions from the neural network that we train. They look accurate. I'm going to be quantitative in a moment. And these are the errors. I think that, again, it so happens that this one, the error is smaller. That's visible by the darker color. But also the length scales on which the error is varying also differ between these methods. So that's just an anecdotal look at what this method does. You can also look, I won't cover it, but it's at the end of the slides if you wish to look at them. This is the median, this is the input that gave the median error at the over 10,000 training data points. At the end of the talk, you'll see the inputs that give the worst case error. So the point of this slide is now to be a bit more quantitative. What I'm looking at is the test error. Remember, I told you that that's a relative error at the beginning of the talk. So it's an average of the error between the true solution, which we compute by pseudo-spectral method to make this comparison, and the trained operator as a function of the volume of data which we use, up to tens of thousands. Let's just focus on the Fourier neural operator. So that's the lowest red curve in all of these because it happens to have the smallest error. What you see here is that the error decreases as I increase the amount of data, as you might expect, provided that the neural network is expressive enough to take advantage of the data available, which it appears to be in this case. And what you see, these four figures here actually correspond to different levels of expressivity. So as we go through these panels, we're increasing the number of parameters which are available to the Fourier neural operator. And when there are enough, you see that the error decreases as a function of the volume of data, like the square root of n, which is given by this curve here. And that is the Monte Carlo rate. Right. On the basis of theory we have for linear problems, we know that we don't expect to be able to beat that. But there are problems where it is not possible to attain the Monte Carlo rate because of lack of smoothness of the functions in the output space. But here the functions are smooth because of the smoothing property of the Navier-Stokes equation, and we obtain the Monte Carlo rate. So this gives an idea as to how much data is required to achieve a given level of approximation error. Now you can combine that with parameterizing the model. And of course, the more parameters you put into the model, the more expensive it is to evaluate. But what you would like is that by being more expressive, and this goes to the theorems that I mentioned to you at the moment, you would like that as you increase the number of parameters, the error should go down. And in particular, as you increase the number of parameters, the cost of evaluating these approximations increases. So these figures, again, let's focus on the red lower curve, which is for the Fourier neural representation of the solution operator. What you see here is that as we decrease the relative error from 10 to the minus 1 down to 10 to the minus 3, the evaluation cost increases, and there's a characteristic shape to this curve. Key point is that, as I will show you quantitatively, this leads to this relationship between error and cost leads to approximations that can be orders of magnitudes faster than standard numerical PDE methods.
1 minute.
Thanks. So let me turn to a different problem in which, as I was said in answer to Edris, rather than mapping the forcing to the solution at time tau, I'm going to map the solution at time 0 to the solution at time tau. This is a statistically stationary regime. And so once you have this, you can compose that operator with itself, and since it's a semigroup, and approximate the solution at any multiples of tau. And it is possible, though I won't show it here, to look at the statistics of the semigroup that you generate this way, and, for example, show that you get correct scaling properties for the energy spectrum. So it's a different test on the accuracy of this method, which I'm not reporting here. But just to finish, to show you the following. So we've used this methodology where we map initial condition to final solution to compute the inverse problem in which one tries to recover the initial vorticity from measurements of the vorticity at later times. And you see here the computations performed by a pseudo-spectral method. These are the predictions by the Fourier neural operator. And the key take-home message is that this inverse problem is ill-posed, and we solve it by a probabilistic method, which requires on the order of 10 to the 4 to 10 to the 5 evaluations of the Ford model. And in so doing, you can compute the entire statistics of the distribution of the unknown initial condition given pointwise observations of the vorticity at a later time. That's like inverting the heat equation. It's a difficult inverse problem, and hence regularized by probability, and hence the solution is a probability distribution, which explains why so many evaluations of the Ford model are required. Key point is this, that using standard pseudo-spectral method, which is already pretty good, as you all know, this takes 12 hours. We can obtain the same level of accuracy in under 2 minutes using this representation of the solution. So I'd like to just leave you with that for these problems, the key value in what I'm doing is speed up. But as I mentioned at the beginning of the talk, there is also the possibility, which we are developing in material science, but perhaps is of interest to your community, of learning closures or constitutive models by the same method. Thank you.
All right, we have a few minutes for questions.
Great talk, Andrew. Just real quick, do you still have the equivalent of an elliptic solve in your numerical method, or do you have a way to beat that in some way?
No, there's no elliptic solve. So
How do you get away?
The only non-locality is the FFT. So what makes this work is the combination of the FFT, so it's a convolutional integral operator, and then universal approximation theorems that if you combine that with pointwise activation, compose it, you're able to approximate arbitrary functions. So it's quite remarkable, really, that you can do that. But there is a catch, which is that you have to generate data in the first place. And so when this will only be useful if you can amortize the cost of the training, which means that the model that you learned has to be used many, many times. Otherwise, the cost of generating data is relevant. Thanks.
Thanks, Andrew, for a nice talk. I have a question which is conceptual. In your first term, in the first part where you change the forcing, imagine that you change the amplitude of the forcing, that below certain value, the dynamics is stable, goes to steady state, and then goes bifurcation for larger values of F. So when you do the distribution of F, you go through bifurcation. How does this manifest itself in the whole thing? I mean,
so because there's a probability distribution on.
So sometimes yes, sometimes no.
Yeah, you're going in the situation you describe. If the probability distribution covers choices of F that give rise to different behavior, let's say there are 2 types of behavior, that will be manifest in a bimodal distribution in the output. But in principle, so this is just purely theoretically, the theorems tell you that you can still approximate that setting. But your intuition is right that if the distribution is bimodal, it's going to be a harder problem. And I don't think in this case it was. So we have algorithmic ways of thinking about that by using clustering. which would embed this method into something combined with clustering. But that's future work as opposed to what we've done.
One more question while Peter goes on.
I had a question. So when you set up a problem, you said that you try to optimize it with respect to some norm, L2 norm of some error. So I'm just wondering, once you've chosen the norm, do you still get good predictions in terms of how you order statistics for the turbulence, or would you need to change that?
Well, we haven't done turbulence, so I just want to be completely clear about that. We did a mildly chaotic Navier-Stokes equation, so I'm not solving turbulence. Just 100% clear about that.
Sure, but
probably none of you are yet either, but I'm definitely not.
Okay. But the
Okay.
question, I guess, still stands.
But no, I understand the question.
Yeah.
What to say about that? So the error metric really matters. So we have some theory for linear problems. What I've done is measured the error in the same, other than the relative versus absolute, in the same norm. So there's a norm called a Bochner norm defined by the expectation. It's the same norm that I used in the training. But you can ask what would happen if you use different norms, and that's the topic of generalization. Tells you something about how well you can predict out of distribution. And you lose something, and you can quantify for linear problems what you lose in terms of rates of convergence and how it depends on the gap between the smoothness properties of the function, this function space that you train on versus what you would want to test on. So that's an important area. Thank you.
No, we are out of time, but we're going to have a discussion section right after Peter's talk. So you can hold your questions until then.
No, that's their computer.
I see. Okay.
Shall I send the IT guys?
Yeah, probably.